Good day, everyone. Welcome to the Chemical Engineering Society's tutorial video series, Che 101. In this video, we will be discussing the Reynolds number, which is first encountered in Momiche. However, expect that you'll be encountering this as well in some of our later courses, but some of the concepts involved in solving for the Reynolds number starts as early as Chicalc. So this will be our outline of the discussion, and we'll basically be defining the Reynolds number and solving a sample problem involving the Reynolds number. And with that, what exactly is the Reynolds number? By definition, the Reynolds number is the ratio between fluid inertial forces to viscous forces. It is a dimensionless group. Basically, when you solve for it, all of its units should cancel out. As you can see on the lower right corner of our slide, you can see the definition of inertial force and viscous force. You can try for yourself if their units are exactly the same, which would mean that the ratio of these forces would indeed have no units. Upon simplifying this ratio, though, we obtain the general expression for the Reynolds number, the product of the pipe diameter, the average velocity and density of the fluid, all divided by the viscosity of the fluid. That is our Reynolds number. So the Reynolds number is associated with different types of flow. We first have laminar flow, a condition that is commonly observed at low velocities. Here, layers of fluid slide by one another, and one way to describe the flow is smooth. It has no swirls nor eddies. In the figure shown, you can see that the streamline of our dye is just straight. Since there are no swirls present in its flow, it can be said that the flow is laminar. Meanwhile, turbulent flow is observed at higher velocities. The flow here is fluctuating, and much like the figure for turbulent flow, there are visible swirls. So how exactly is the Reynolds number related to these types of flow? Quite convenient, actually. There are certain ranges of the Reynolds number that indicate the type of flow. For lower Reynolds numbers below 2,100, the fluid is undergoing laminar flow. Between 2,100 and 4,000, the fluid is in transitional flow, which is a region that is between laminar and turbulent flow. Above 4,000, the flow is considered turbulent. However, do note that different textbooks define the Reynolds number differently. The Perry's Handbook, for instance, defines turbulent flow for Reynolds numbers above 5,000, while there are also books that say 6,000 or even 10,000. Now, let's head over to a sample problem for Reynolds number taken from John Coppolis' 5th edition. Water at 30 degrees Celsius is flowing at the rate of 10 gallons per minute in a pipe having an inside diameter of 2.067 inches. Calculate the Reynolds number using English units. Let's start with the given values. I have gone ahead and emphasized the given values, and we are given the temperature and volumetric flow rate of the fluid, as well as the diameter of the pipe. From the given temperature, we can simply get the density and viscosity from tables typically at the back of chemical engineering textbooks. Once more, we are being asked to solve for the Reynolds number. Our first step in solving this problem is actually redefining our Reynolds number. Since our given flow rate is a volumetric flow rate, we can express our velocity in terms of the volumetric flow rate. We can also define our area in terms of the diameter. Our general assumption here, unless stated otherwise, is that we are dealing with a circular pipe, hence our area is simply the cross-sectional area. This is defined as pi r squared or pi over 4 d squared. We can now plug these relations into our Reynolds number expression from earlier, and we will be getting this expression, which we can actually simplify further. Now, here is our Reynolds number expression in terms of the volumetric flow rate, and now we can proceed to solving for the Reynolds number. Our next step is simply just directly substituting our given values into the expression. Again, take note that for the density and viscosity of water, we can simply just take the values from the respective tables. These values are from Appendix 2 of John Coppolis' 5th edition, and luckily our given temperature is actually on the table immediately. In the event that your viscosity or density is not on the table, you may have to perform interpolation. So this large expression on your screen is simply just a complete substitution of our given values. Take note that your units must cancel out. Generally, for English units, I advise converting all mass values into pound mass, lengths to feet, time to seconds, and so this huge expression is simply just a complete substitution of our given values. Take note that your units must cancel out. So generally for English units, I advise converting all mass values into pound mass, lengths to feet, time to seconds, and such. The Reynolds number is also quite important in determining other quantities and dimensionless groups. However, I'll be focusing more on those discussed in Momeche, such as the Moody diagram. The Moody diagram relates the fanning friction factor with the Reynolds number, and typically you'd be using the tie lines for the roughness diameter ratio to obtain the fanning friction factor. So the fanning friction factor itself is another dimensionless group used to define or determine rather the effects of friction on the system. So in Momeche, you would typically encounter this dimensionless group when solving for skin friction, though typically you would be using relations like the Colebrook-White equation over the Moody diagram. With that, I'd still like you to try looking for the line corresponding to the Reynolds number we got previously. So you can pause the video before we proceed to showing where the line is. And here's where the line is actually located. And depending on the value of the roughness diameter ratio, you can get the value of your fanning friction factor. There is also another chart that relates the ratio between the average and maximum velocity of a fluid with the maximum Reynolds number. And this is typically solved by using Umax instead of U bar for the velocity component of the Reynolds number. So this is typically used for problems involving flow meters such as the Venturi meter. Now, here's a brief summary of what we just discussed. Take note of these as it could definitely help you in understanding how to use the Reynolds number. If you have any questions, you may contact the Chemical Engineering Society through these channels. That concludes my presentation, and thank you very much for listening.